Okay, yeah, hi everyone. So today I am presenting properties of the neural network related to frequency. And specifically, I'm presenting something called a spectral bias. Basically, spectral bias explains why neural network learns low frequency info. Okay. How do I go back my slide? Okay. Yeah, so basically there are three topics here. The first one is the fundamental theory about why neural network learns low frequency information exponentially faster. And this is explained through the neurotangent kernel and the spectral bias. And the second subtopic is about uh, a specific property of modern CNN. Uh, yeah, we'll look at later. And the final subtopic is about designing frequency-aware architectures. So, okay, so the part one is about the underlying mechanism why neural network learns low frequency information exponentially faster. Uh, just a quick disclaimer that this topic is extremely math heavy, but I try to remove all the math and try to, directly introduce the conclusion from those papers to make it more intuitive and easier to understand. But I highly recommend you to look at these original papers. The first one is the neurotangent kernel, and second paper is on the spectral bias of neural networks. They have very solid mathematical analysis on their conclusions. Um, so in the analysis of the property of neural network, people discovered a phenomenon that lower frequency informations are always learned first. Deep neural networks, they always prioritize learning simple and global patterns first, and they struggle to fit this high frequency information or noise. And this phenomenon is also known as spectral bias. And here's an example from their paper. So this training example is just a superposing of different sine waves on different frequencies. And you'll see that as the and this is how the neural network evolves as the training iterations goes larger. You know, you can see that at the early stages, the neural network is trying to uh, fit a very general shape of this sine wave. And but gradually as the training goes, the neural network is fitting the higher information uh, better and better, and eventually it can fit the training example perfectly. But it always starts from um, learning the low frequency information first. Yeah. And so here's another experiment. Uh, so this experiment also like explicitly decomposes all the um, frequency components in the learning process. And so you'll see that um, on the left figure, and when the training iterations is less than 10,000 steps, the magnitude of the low frequency information converges to one almost like instantaneously. And that means the neural network learns this low frequency information almost like instantaneously. Yeah, but it struggles to learn those high frequency information only until uh at the very late stages of the training process. Uh, and at the second figure, so the researcher tries to explicitly increase the magnitude of the high frequency information in the training example. You can think of like hard coding some sort of scaling to those high frequency informations, but this phenomenon is still there. The neural network still learns the uh, low frequency information first. So to understand all these phenomena, there are a lot of like basic concepts we first need to introduce. And the first basic concept is function analysis. So in standard linear algebra, a vector can be seen as a list of numbers. But in function space, a vector is an entire function. And so the question is, can functions actually compose some sort of space? The answer is definitely yes, because uh, the functions also satisfy the axioms of vector space. You can add two functions and you can scale one function. So the supports the basic calculations, the basic axioms of the vector space. And um, so a standard vector in in the uh, a standard vector with three dimensions, you will need three numbers to describe it. But to describe a continuous function, you will need to know its value at very possible x. And since there are like infinity many points between 0 and 1, and you need an infinite list of numbers to describe the function. So this, well, you can think of it like to describe a continuous function, you need like infinite combinations of some basis functions. And these infinite functions span in the Hilbert spaces. And is and the Hilbert space is infinite dimensional. And there's also another uh, classical machine learning concept called Gaussian process. So instead of like assume a specific shape of a function, a Gaussian process just assumes the function itself is a random variable defining a probability distribution over all possible functions that fit the data. And you could see from this visualization, at the initialization, the Gaussian process is in your network as a combination of basis functions, and these combinations are random. But as the neural network sees more and more data, uh, this kind of distribution gets more and more deterministic, and especially at the data points. The data point is like a pin, like connecting all these basis functions. And in the end, we'll see a band covered on the observed data. And the mean value of this band is described as a mean function. Yeah, and the uncertainty um, and the width of the band defines the uncertainty of the combination of basis functions. Yeah, so the Gaussian process is defined by two things. The first one is the mean function, as we just before, and the second thing is the kernel function that defines the similarity between 2 points. And So here is the most important concept from the neurotangent kernel paper. So they have some assumption for the infinite width limits of a neural network. So imagine that we have a neural network that is infinitely wide. In that case, so during gradient descents, the weights of that infinite wide neural network changes infinitely small during gradient descents. And because they move so little, the weights move so little, the local linear approximation of the network, or you can see, or you can think of it like a finite subset of the parameters stays constant or near constants. So they call it tangents. And in this process, I mean, under the assumption of infinite width limits, this means a complex and nonlinear neural network behaves like a SVM model. Um,
Is it a finite subset of the layers?
yes, finite subset of the layers. And and you mean the word tangent itself?
Yeah, what's the connection between tangents, the geometry and this, like, is there I just don't see it. Yeah, what does it mean, I guess, maybe, are you saying any finite subset, like?
Yes, basically any finite subset.
Oh, okay.
So
Yeah,
like any function, you can approximate it with a linear function. If the linear function is a tangent at that particular point. So instead of like actual function value, you just go along the tangent. So it behaves like just approximate it with the linear.
makes sense.
Yeah, and
It's a tangent of all the entire subset?
so at a point. So at a point means like one particular set of values for those infinite things for one particular set. If you want to say how those change, or in what direction would it change, you just go along the tangent in one step. Instead of going one step along the function, just one step along the tangent.
I see.
So like if you have a curve, something like this, and this is that specific
Yeah.
point, you draw a tangent over there.
Yeah,
And if you want to find like the function value, like let's say in this direction, you just go along the tangent and you just ignore the height.
I see. So he's saying that you take a finite subset of neurons, you compute the tangents, approximation of those neurons?
Yes, I think, yeah, I think that's how I understand it.
Change at that point. Like
Yeah.
during gradient descent, how would those values change for the particular loss function? And then you just approximating that.
Okay, I see.
I think it's like a local curvature of that neural network stays constant.
Got it.
Yeah, yeah,
Okay.
yeah,
Yeah, it's infinitely many width, you have the
I see.
function.
That makes sense now. I guess.
yeah. So, and this gives a very, I mean, under this infinite width assumption, this gives a very good property because that means a complex nonlinear neural network actually behaves like a linear model. But specifically, it behaves like kernel regression, like SVM. So the model itself is linear, but with a nonlinear kernel, just like what SVM does. And that nonlinear kernel is called neurotangent kernel.
So this is a specific kernel that you have to use? Specific shape of the kernel?
Yes, Alvin.
Work with such kernels, then you can prove that it's nearly linear.
Yeah.
And also because you're making the Gaussian process assumption. Like instead of the Gaussian process, if you make some other assumption, then it will be just good. But I think because of the Gaussian process, the kernel becomes like has a specific functional value, right? I'll take a specific function, the kernel.
So in this paper, they think the neural network is like a Gaussian process itself when the width goes to infinity. And at the initialization, that kernel here defines the neural network is actually the Gaussian covariance matrix. But as the training process moves forwards, the kernel is actually the neural tangent kernel of the neural network itself. It's replaced by the neural tangent kernel of the neural network itself. And the neural tangent kernel is actually well, it's a function about its derivative. I think I will introduce it now. Yeah. So there are two ways to define the neural tangent kernel. One is the function perspective. Another one is the matrix perspective. And actually, I'm defining it in the matrix perspective here, which is much easier to understand. So if your neural network is parameterized by theta, and then the gradients with respect to all the parameters given some input x is this vector. And now suppose our data set has like n samples, and we can stack these gradient vectors into an n by p Jacobian matrix. So the neural tangent kernel can actually be represented by the Jacobian matrix dot product, the transpose of the Jacobian matrix, which gives us a size of n by n matrix. And each entry in that matrix is the inner product of this derivative pair. But I think so, but it's a personal perspective. I think this one is just like it's only suitable for theoretical analysis because it is kind of impractical to calculate this matrix. It's kind of computationally infeasible here. Yeah. So in that case, we can connect all these things together, the neural tangent kernel, the Gaussian process, and eventually the convergence speed. So in linear algebra, an eigenvector satisfies this property. But in function space, an eigenfunction, basically it is just like the eigenvector, satisfies this integral property, which is, you can think of like a equivalence equation to the property of eigenvector. So you can think of like we have a kernel. So in linear algebra, we say that we have a eigenvector and we dot product the matrix A with this eigenvector. It is equivalent to scaling that matrix. Scaling that eigenvector along some dimension. Along a specific dimension or its own direction. Yeah. But in your tangent kernel, this one is replaced by this integral operation here. So instead of a matrix A, we have a kernel operator. And in our case, it's the neural tangent kernel. And for the eigenfunction phi, this is the basis function in this space, in the function space. Yeah, and the eigenvalue is a scalar or a weight of that basis function. Okay, so here is an interesting property is that since we can write the neural network in this form, where a neural network can be written as a combination of different basis functions, where the weights of each basis functions evolves as the training goes. This t is the training time. the paper tells us a conclusion that the weight changes is in a as a exponential connection, exponential magnitude connection with the eigenvalue defined in the eigenfunction decomposition. And so I think this one is much more straightforward. So the error rates has an exponential magnitude connection with the eigenvalue of the Gram matrix. And the Gram matrix is the neurotangent kernel, comes from the neurotangent kernel, and the T is the training time. So, and another conclusion is that the neural network, the eigenfunctions with large eigenvalues are usually smooth, low frequency waves. And because they have these smooth and low frequency basis functions, they tend to have large eigenvalues. Their error reduction rates is actually exponentially faster due to this larger eigenvalue term. So this larger eigenvalue term in the function space acts like a internal learning speed for different basis functions. And since low frequency basis functions, they have larger eigenvalues. Their error reduction rate is exponentially faster than those functions with smaller eigenvalues. So the conclusion is that the eigen decomposition of the neurotangent kernel maps large eigenvalue to low frequency eigenfunctions, and the error decays exponentially faster because those low frequency functions, low frequency components, decays exponentially faster because they have larger eigenvalues. Okay.
This is the first paper.
Yeah, this is the first two paper.
Kind of insight in how long a neural network would need to be trained, how many steps are necessary, the relationship of the signal to training time, or what would science? Is there
Yeah.
practical value to this kit?
Yeah, the practical value is very obvious. So suppose like you're training some sort of computer vision model in 100 epochs, and for the first epoch, you probably learned 90% of the low frequency information. But for the rest 99% epochs, you are probably learning the rest 1% or 10% of the high frequency information. Yeah.
So when you train now and look at your learning curve, can you turn it around and use it also as a recipe when you can break up? Or how long you have to train, or a relationship to your signal?
I think the conclusion here is that this neurotangent kernel theorem explains why it is inevitable that high.
No, that's
Yes,
understand,
yes,
but
it
it's
is
an
inevitable.
explanation, right? Whatever, we learn first the low frequencies, then we learn the high frequencies. And that applies to any neural network, or what is this?
Yeah, it's basically applying to any neural network.
Whether CNN, whether fully connected.
Yes, it's a general analysis, yes.
So what is this neural tangent kernel then used for? Just for explanation?
Yeah, I think it's more theoretical where like if the wind goes to.
Okay.
infinity.
No, okay, so it says you first learn the low frequency, then you learn the high frequencies. Okay, fine, and then, just
I-
one, if you look at your training curves, right?
Mhm.
Whether this could be turned around in your recipe now. Do you see what your signal is, or can you
Yeah.
make some conclusions? Yeah,
I think,
or also during testing, could we say something,
Yeah.
comparing training testing?
I think the neural tangent kernel also gives us a new perspective to analyze the neural network in this way, in this side. Because in the infinite width limits, it is just seeing neural network as a linear model, but with that nonlinear neural tangent kernel. And so that's all its properties are basically concentrated on that kernel. So if we can do some more analysis on that kernel itself, we could have some more insights on the neural network. Yeah. But I
Yeah.
think,
Yeah, sorry, Hawen, it's really, really interesting. I love these topics. I have one question I think I'm missing there. So I love the similitude. I mean, the way that they explain this by getting to a linear model. I think missing the point where you just to confirm, when you say I take a network with an infinite number of units, that's the connection with the linear model. That's where you think it comes, if I understood correctly, with the fact that you have an infinite number of units that gets you closer to a linear model, or
the linear model assumption comes from the definition of tangents, because as we discussed, the local approximation of the neural network, or a subset of the neural network's weight, barely moves, so that the tangents or the local gradient approximation of the neural network stays constant. So if everywhere is like a constant, has a constant gradient, right? Suppose like every subset of the infinitely wide neural network has a constant gradient. It is exactly like a linear model, isn't it?
okay, got you now. Thank you. This is amazing, by the way.
Yeah.
It's okay. And Matthew also wants to ask something. Can you?
Yes, I also had a question. So this is a really interesting topic. Thank you for arranging the presentation. One question I had in mind was with this approach, are you targeting to reduce the computation complexity? You don't have to do nonlinear kernels. Is that one of your targets and goals?
No. Sorry, I think it's just a theoretical analysis here, because it, like what I said, it would be impractical to calculate this kernel
But
matrix,
yeah,
right?
yeah. But in the future, like if uh, could this obstacle be somehow also addressed to reduce the computational complexity? Because then you don't have to deal with nonlinear kernels, or that's out of the picture.
You mean if we have like enough computational power to compute this whole gram matrix?
Or somehow simplify it somehow.
Uh-huh. I would say, I would say it would be a promising direction, but I don't know.
Okay, thank you.
Yeah.
So I had a question, like, what is the loss function that they used? Like when they were training the network, what was it just the L2 loss, or did they try with like a bunch of losses?
I think it's not about the loss, it's about gradient descent.
But like
But
gradient
right.
descent like depends on the loss, right? Because you take the gradients. The reason I'm asking is if it's just an L2 loss, like if it's just the square,
Mhm.
then you might get different solutions versus if you also, let's say, were to like penalize the higher powers, like raised to 3, raised to 4, and so on. That might actually force the model to give more weightage to also like the details, like more of the details.
Mhm.
and so on, or will the curve look the same irrespective of the loss function or not? Do you
I think this empirical experiments actually does similar things because they explicitly increase the magnitude of high frequency information in the training example. I think it's somehow equivalent to, like we said, uh, giving higher weights to those uh, giving higher weights to high frequency informations by increasing the orders of your loss function or something.
Like the weights, son.
Yeah,
But will that be equivalent to like
but
using?
but from
loss function? I don't know. I don't know honestly if there can be made an equivalence between the two. Like the whole Gaussian assumption, why does it like come to a Gaussian process and the kernel is like the covariance matrix? Does this also like work for like different assumptions? Like if you, let's say, instead of a Gaussian assumption, you made a Laplace assumption or something of a higher power, would it still make a difference? Or would this still hold?
Hmm. I don't think I can answer that for now. Yeah, yeah. Sorry, I don't think I can answer them for now. Yeah, but I think since they empirically try to increase the magnitudes of high frequency information, the neural network is still reluctant to learn high frequency information first. Yeah. Okay. So I think we can move to next part. I think this one is much more interesting and not that math heavy.
Because Jan is trying to reconstruct the sound from event signal, so he has to wait for a while he gets the high frequencies.
Yeah. So this is an interesting paper, making convolution networks shift invariant again. And this paper draws an important observation is that current in modern convolution networks, we have some downsample layers like max pooling or stratic convolution or average pooling. And these downsample layers actually violates the Nyquist Shannon sampling theorem because in order to, preserve the information on all the frequency bands, we have to sample at a rate that is twice larger than highest frequency in the components or the feature map. But the max pooling sampling rate actually does not satisfy this theorem because in the feature map, there are many high frequency information like textures, which max pooling cannot match. So in that case, this high frequency information actually alias after we do downsampling, and that will cause instability during training. And the paper actually start connecting this sampling theorems. I mean, this paper analyzed this sampling theorem violation through a property called shift equivariance and shift invariance. So we say a function is shift equivariance if the shift operation and the function itself or the feature extraction process are commutable. And we say a representation is shift invariance if shifting the inputs results in identical representation. So they actually they actually tried it on existing dataset like CFR10 or ResNet by shifting the images along the diagonal direction. And they found out that by shifting the image along the diagonal direction by some specific pixels or units, the performance of the convolution network actually drops significantly. And the convolution network actually suffers from this shift. The performance is, you see, in this example and in this example, the model cannot even identify what the object is, but sometimes it can correctly classify that image. So that means shifting the image causes some drastic change in the internal feature map. So they have a conclusion that the modern CNN are not shifting invariants. Yeah.
Sorry, what's the y-axis on those plots? I can't see it here.
Sorry, which one are you
The
saying?
plots, like
Probability of the correct class.
Why is it going up and down? It's very.
Because it's been shifted along the diagonal direction by some units.
Yeah.
By some unit pixels.
So I thought the more you shift it, the worse it gets or something. It's,
Yeah, but it's oscillating, right? Yeah.
So shift invariant. The shift invariance means, for example, that if we have classification, no matter where the object is, that track what you recognize that it is a peak in the image. Now equivariance means if it's at some location, you shift it to another location, that then at that location it detects that object. Yeah.
No,
It still detects it, but shift it also to that location. That's equivariance.
No, I think your understanding for shift invariance is correct. But for shift equivariance, it is saying that the feature extraction and the shift operation are commutable. That means if you first do the feature extraction, then you do the shift, and then you switch these two operations. The eventual feature generated are identical. So the two operations are commutable here. So in this equation here. So the specifically look at the downsampling layer, which violates the sampling theorem. So in the original paper, they actually deconstruct max pooling operation into two steps. So in general, when we're using max pooling, we set stride to 2 and the kernel size is 2 as well. Because we want to, downsample and extract some, most distinct feature in that local area. But this is equivalent to a max pooling of 1 strides with the same kernel size, and then followed by a subsampling operation. And for this first step, which is the stride 1 max pooling, it is actually shift equivariant, but the subsequent downsampling process actually breaks the shift equivariance property and causes very heavy aliasing. So their solution is quite straightforward. So since those high frequency information in the previous feature map alias in the downsampled feature map, their solution is very simple. They just blur out the previous feature map. And in that case, they somehow directly remove the high frequency information in the previous image so that they remove the aliasing artifacts in the subsequent feature map. It is like a cleaning process. So they add a blur kernel by decomposing the max splitting operation. And yeah, so we still have a subsampling process, and the shift equivariance property is also lost, but the aliasing problem is reduced or even removed.
So they adopt this grid signal processing. When
Yes.
sample first, Gaussian filtering.
Yes, like a low-pass filter.
Yeah.
Apply a low-pass filter to filter out the high-frequency information in the previous feature map so that they prevent the aliasing in the downsampled feature map so that the extracted feature will be more stable and clean. So this is a Python code of blur pooling. And yeah, so they have a very simple binomial kernel, and they expand it to 2D, and they just do a strided convolution using this low pass filter. And the results, the result shows that it improves. It has a massive gain in shift invariance property, as or not the shift equivariance property, because the subsampling process always destroys the shift equivariance property, but the shift invariant property is actually preserved. That's the title of the paper, right?
For classification.
Yes, but just for classification. That's actually that's the thing actually what I want to say. I don't think it is suitable for tasks like segmentation or image restoration or image reconstruction because we directly remove all this high frequency information. Yeah, and if we just remove them, the network will never see them during training. And the tasks like image restoration or image reconstruction or segmentation, these dense tasks, they require high frequency information, right? They require to reconstruct the detail of the object, like the texture or something. So I don't think it is suitable for using dense task. But for classification, I think the performance improvement makes sense.
So they book the results for this image classification task.
Yes, and also the feature consistency. Yeah.
Are people using this already now for classification tasks?
You
With
mean
blur kernel?
in our project or?
No, I mean, how old is the paper?
Oh, this is very old. This is 2019.
Have people adapted this concept now for classification?
I'm sure there have to be approaches that allow the model to either be shifted variant or shifting equivariant, but not one or the other, you know? Because like segmentation needs both, right? Like segmentation needs some representations that are invariant to shifting and some representations that are equivariant to shifting, but like is that done? Like, because this is useful for understanding, but it's not useful for like a wide variety of tasks, right? Like, my questions just have to be follow-up works that allow a model to have one or the other property, but not necessarily restricting it to one.
I haven't looked at the subsequent works actually, but I think I think you mentioned an interesting point is that like tasks like segmentation requires probably both of those properties.
Exactly.
And I think somehow the architectural design of UNets somehow alleviates this because UNet gives us a very very strong and symmetric spatial connection for those features, for the hierarchical features.
Right, yeah, because
I think that somehow, alleviates this kind of loss of shift equivariance.
yeah, the stick connections kind of allow you to keep high frequency information.
Yeah,
And ups-
to
downsampling.
to allow it to directly flow to the decoder. Yeah. Uh-huh.
This isn't a question, just rather an observation. Since we were talking about other tasks of this paper, actually on page 8 of the paper, they do say they do image generation too. So that is interesting.
Oh, really?
Yeah. I mean, not for like super resolution, right?
Uh-huh.
But it is just an interesting observation.
Mm-hmm.
And they do outperform slides.
Cool.
But I guess it's 2019, so maybe.
So maybe
Yeah, not,
before the VIT
yeah.
time, yeah. But right now we have Vision Transformer. Things have changed a lot.
Today is the
Yeah.
But I think like for convolution network specific, they started using just strided convolutions, right? Where the image was downsampled and it's like the network learned its own pooling function. It's
Yeah,
like
yeah. I
pooling.
think modern ResNet are using that.
Yeah, they just use strided convolutions.
Yes.
So no specific max pooling there. Or
Yeah.
any pooling function that you look at. The model just learns the best pooling function for that task.
Yeah, I think strided convolution actually makes sense because yeah, it is kind of like a learnable downsampling process.
Yeah.
But still, I think it somehow it cannot circumvent this process, this downsampling process. So there is still there is an internal sampling frequency here. I think it's like 50%. Oh, sorry, 25%. Right. Because we only preserve 25% of the local region. So there's an internal fixed sampling frequency for all downsampling processes. So maybe high frequency informations will still alias, even with a learnable strided convolution. So I think that's also the reason why they explicitly decompose the downsampling process.
So they do already on pooling, they learn how pool is saying, what about the plane domain? When we work over longer seconds, have they also learned already how to pool? Would it make sense to apply this concept of blurring the time domain? Like when we talk about PDF signals, for better action recognition than basically.
But I think all convolutions are strided now. So I don't know if it helps or not specifically, but like I think there was one paper which showed that strided is just better for the timing. But I don't think they did an analysis like this. Like that, I agree with them. Like there's an inherent like downsampling that's happening, irrespective of whether it's because of strided or any learned, even any learned downsampling will actually affect the or will cause AUC. So I think we still lose information there, even if it's strided convolutions. But it's better than max pooling, I think, for downsampling. I'm not entirely sure like how much information is lost.
I think we're not losing information. We're aliasing high frequency information for all downsampling operations.
Right. For you kind
because of the internal downsampling rates.
Right. But at the output, you don't quite see those high frequencies. Or do you think that information is still there, even though
I think with the supervision of loss function, the network can somehow learn to recover some of the high frequency information. But even with that, all high frequency informations are lost in this downsampling process. Yeah. It's just, it is learned through the explicit supervision from the loss function. Yeah, so the conclusion, I think the conclusion is very elegant and trivial. So since downsampling are not shift equivariant due to violation of the sampling theorem, we just directly remove the high frequency information by blurring, which removes the aliasing artifacts. And this gives us better performance on classification tests. Yeah. Yeah. So, and the last part is about the frequency aware architecture design, where we somehow specifically make the model learn different frequency information in the feature map. And this is a recent paper from CVPR 2025. It's called Frequency Dynamic Convolution. And the primary contribution of this paper is that it somehow adopts the idea of filter bank by explicitly assigning each learnable kernel with a specific frequency. And they do some linear combination of all those filters in that bank, so that this entire block can attend to all the frequency bands in the previous feature map. So here is their architecture design. So you can see that there are three parts of it. So in the first parts, it is like a preparation of the filter bank. They have a learnable parameter vector, and they assign each the learnable parameter vector with the explicit Fourier indices. And that is the something like a frequency assignment stage. And then they do inverse discrete Fourier transform to transform this learnable parameter vector into a regular convolution vector. And that's the first stage. And they also calculates weights, linear weights for each of the filter using attention. This assigns each of the filter with a single weight, and is calculated from attention. Yeah. And
Sorry, just to clarify, so we're learning, just to make sure I understand what you're saying, given the Fourier coefficients, we're learning just like 3D kernels for convolution.
Sorry, I don't understand your question.
It's the kernel,
yeah, it's the kernel.
Yes. This kernel and this learnable parameter, they are all n dot parameters. They are learnable parameters. Yeah. And we know that the IDFT operation is also differentiable, right? So this is still a valid operation. Yeah. So, and at the second stage, so after they do a linear combination of all those filters, they calculate another attention matrix by explicitly considering the spatial relationship of all this of all the image and all the filters. So, and yeah, they just do a pointwise product to merge, sorry, not merging, by assigning each of the parameter with its spatial weights. So they have an adaptive kernel. Okay, so And in the final stage called frequency band modulation, they first do a discrete Fourier transform of this kernel into frequency domain, and they explicitly decompose this kernel into different areas. And I think in Fourier domain, these different areas corresponds to different frequency components. And they do a discrete Fourier transform of the original feature map, also put it into the Fourier domain. And they use the decomposed kernel to directly interact to make them directly interact with the feature map. And yeah, and after this interaction, they do inverse discrete Fourier transform to transform back into the pixel space or feature space. And they do a final convolution operation on this feature space. And you'll see that for a specific kernel, the feature space have distinct representations for different frequencies. And they eventually do an element-wise addition to compose all these features at different frequencies. Yeah.
What is the idea?
It's in inverse discrete Fourier transform.
That is modular. The idea.
Yeah, the IDFT is a deterministic process.
A learnable parameter like the white box, and then the blue and the orange is showing Fourier indices. That's a number, right? So
Mhm.
the learnable parameters, the first white long box, where does that come from?
Which one?
The
The
very left. Before
very left.
Yeah. Is that?
This one?
Yeah.
This is just initialized as learnable weights, right? And dot parameters.
So it's a initialization of a weight into IDFT. Into a
Yes,
space,
yes.
And use that as a.
Yeah, you can think of like they're preparing a bank of filters. And each filter is assigned with explicitly assigned with a different frequency.
So the explicitly assigned part is assigned by the disjoint Fourier indices.
For indices, yes, exactly, yes. Yes.
So you're learning here an architecture that's better suited for signals that have a good signal representation?
I think probably yes. It's like a general purpose module to explicitly learn different frequencies from a feature map. Yes. Yes.
Thank you.
Mhm.
Especially as attitude, texture,
Mhm.
or pattern behind, pattern emotion.
Yeah, yes.
Array.
Yes. They actually make it a pluggable module that can be plugged into any model.
Oh.
And their total number of parameters is 3.6 million. So we'll see this is a semantic segmentation task. And the original ResNet 50 has parameters around 66 millions. And with this explicit frequency dynamic convolution block, the parameters goes to 70 million, and the flops almost doesn't change, and they can improve the final performance a lot. So this is I would say it's a very powerful module that can explicitly disentangle different frequencies.
can disable frequently, so it should be well suited for semantic segmentation.
I think so, yes, because they're evaluating their tests on dense tests. Oh, sorry, they're evaluating their models on dense tests like semantic segmentation.
So any dense task, that's your hypothesis.
I think so, because any dense text could, I mean, as long as the dense set requires very fine details like segmentation, I think that then this module would be very helpful. And here is a visualization of their filters. So the left image, or sorry, the image in the middle is some previous work. They decompose their filters, and they found out that those filters are somehow identical and duplicate. And they cannot learn very distinct frequency informations. But after decomposing their own filters, they found out that the frequency attention in the Fourier domain actually varies a lot, and that gives it a diversified attention to different features. Different frequencies in the feature. Okay, so to summarize our topic, so we introduced the spectral bias, where neural networks are naturally biased towards low frequencies through the neurotangent kernel analysis. And we also talk about the topic of downsampling convolution. And the current downsampling operation ignores the sampling theorem, which causes aliasing and instability. And that's where the anti-aliasing downsampling kernel, which is a blur pooling, come in. And finally, we talk about some frequency-aware architecture that can explicitly manage the spectrum of different frequencies. And that's it. That will be all for my presentation.
Okay, thank you.
Hi, I have a question for